This is a challenging binomial distribution question. First things first, we've got a train that's either late or not late. The probability that it's late is 0.15. That's going to be our probability of success, P. We're told that the events are independent. Then for part one, we have that the number of days on which it's late is denoted by capital Y. And there are 450 days over the period, so Y will follow a binomial distribution. Number of trials is 450. The probability of success is 0.15. Then we're asked to find A such that the probability that Y is bigger than A is approximately 1/6. This is kind of flipping the problem on its head. Normally we work out the probability that Y is bigger than 3 or something like that, but here we have to work out what A is. Now there is no inverse binomial distribution. If this was a normal one, what we would do is we would make it so it's less than or equal to A. And by the way, this is going to be 5/6 because these two together must add to 1. If it's greater than A or less than or equal to A, it must be one of those, so it's certain that it's one of those, so we can do 1 minus 1/6. And this is 0.83 recurring, in fact. I'll just put 333. So if this was a normal distribution, we would then just use inverse normal, but we don't have an inverse binomial distribution. So I'm going to show you two methods for how you can work out A. Method 1, first of all. Method 1 is probably the easiest to understand, and it's actually the way I did this problem when I first saw it, and it is in fact to use just trial and improvement. Just try some values of A such that we'll get 0.8333 or thereabouts. So if we go to distribution, it's going to be binomial CD. By the way, this is a really complicated thing on the left, adding up lots of probabilities. So we have to really use this kind of numerical approach that the calculator brings. Binomial CD, you can use the list function. Now you can just try some numbers. You can do sort of what's called a kind of a decimal search. You just narrow down until you get close to 0.83 recurring. The only thing I'd say is because the probability is very small, we're expecting the probabilities to be high for a small number of successes. So I'm going to go, maybe I'll just try go up by 50s to start with. So 50, 100, to see what that gives, because I'm not expecting it to be very high. And then N is 450, P is 0.15. And we see that 50 is actually very small. The 100 one is very, very big. So it's going to be in between those two. So maybe I try 60, 70, 80. Let's go with 90 as well. That's the great thing about this list function. You can just work out lots at a time. So probability that Y is less than or equal to 70 is about 2/3. For 80, it's getting close to 1. It's going to be between 70 and 80. So now let's just go up by 2, 72, 74, 76, 78. Okay, I don't need to necessarily write this down. I need to write down some crucial things in a minute. All right, so it's going to be between 74 and 76. And we'll ignore that one. So there we have it. We've got one that's just slightly less than 0.83 recurring and one that's slightly more. So it's going to be one of these two. I think it's slightly closer to 74, so that's what I'm going to put as my answer. So I'm just going to write trial and improvement. The probability that Y is less than or equal to 74 is 0.8229, which is less. Maybe I'll just write too low. 0.8542. Too high. So it's closest to 0.8229. So A equals 74. And that's my answer. Note, I think the mark scheme lets you get away with 75 and even 73. Like all of these would be approximately 5/6 and hence 1/6 for this first bit. But I've just gone with the one that's the nearest to 0.83 recurring. Okay, it's a really solid approach. You know, you might think, oh, I don't really like it. I have to try numbers, but it works. And this is a complicated expression on the left. Method 2. It actually comes back to what I was saying right at the start of the question. If we had a normal distribution, this question would be very quick because we could use the inverse normal function. But we know that we can approximate a binomial distribution with a normal distribution if we have large n and or p close to 0.5. So we do have a very large n here, and so let's go for it. Normal approximation. So y is going to be approximately a, which follows a normal distribution, with mean equal, this is given in the formula book, but it's actually the number of trials times the probability of success. So 450 is the number of trials times the probability of success. That is the mean number of successes, 67.4. Sorry, 67.5. And then the variance is equal to NP times 1 minus P. This is the probability of failure. Sometimes this is called Q. But I just take my mean and I'm going to times that by 0.85, which gives me 57.375. And just to write down that means the standard deviation is going to be the square root of that. So the probability that y is less than or equal to a is going to be approximately the same as the probability that capital A is less than or equal to a, which is approximately equal to 5/6. Now, I just want to mention one thing. Technically, when you go from a binomial to a normal, you should do a continuity correction because you're going from discrete to continuous. There's a few reasons why I'm not going to do it in this case. One, it's only 3 marks. You know, there's no way we expect to do a continuity correction here. 2, this is an approximation question. It's just that the probability is approximately 5/6. So we've already lost accuracy. So doing a continuity correction is not going to be that much more helpful because of this. We're only looking for roughly the value of a. I think my only other thing to say is that, like, because n is large, the continuity correction would be small anyway. And I'm just overcomplicating it and gonna, potentially confuse you because there's already quite a lot to take in. So we're actually ignore. I'm just gonna write down ignore continuity correction. Okay. We now go back to distribution, but it's going to be inverse normal. The area is going to be exactly 5/6. The standard deviation and the mean is 67.5. And we get 74.8. Okay, so A would be 75 to the nearest whole number, which I did say was accepted on the previous method anyway. Just for info, I'm not going to go into this in detail, but if I had done a continuity correction, then I would have added 0.5 to A here, so I then have to subtract 0.5 from 74.8 to give the answer, which would be 74.3, which would then round down to 74. So it's not that it's given a different answer, it's just that we didn't do a continuity correction. Okay, I hope you're happy with that. That's quite a tough start, it's got to say, but it's only going to get tougher. Let's look at the next part. So part 2, we've got an expansion involving terms 0.15 to the r, 0.15 to the r plus 1, denoted as such, and we're asked to show a relationship for them. So I'm just going to scroll down the page, I've copy and pasted this, and I'm also going to copy and paste one other thing, which is the binomial expansion formula. This question links in binomial distribution to the binomial expansion. So in my case, A is 0.15 and B is 0.85 and N is 50. And if I want the term 0.15 to the r, it's the term which has A to the r essentially. I'm going to kind of take this but sort of modify it slightly. So TR is going to be N choose R, so it's going to be 50. Do you know what? I'm gonna kind of swap it around. So I'm going to say that this is just the way this formula is written, because it's got B to the R. Why don't I say that this is B and this is A? That just makes it more logical when I now apply this formula. So it's going to be 50 choose R. Yes, I'm working out the term in B to the R, which is 0.15 to the R. So it's going to be 50 choose R times 0.85 to the 50 minus R times 0.15 to the R. Okay, oof. This in fact is a way of writing down the probability that my random, say I've got a random variable, is equal to R for my binomial distribution, because it's I'm multiplying along my tree diagram here, and I'm multiplying by all the combinations and such like. But I'm not going to get into any more detail on that now. And then T, I'm going to sort of do this question from the binomial expansion perspective, but they are the same thing. TR plus 1 is then going to be the term with 0.15 to the R plus 1. So it's going to become 50 CR plus 1 times 0.85 to the 50 minus R plus 1 times 0.15 to the R plus 1. Okay, I hope that makes sense. These two powers will add to 50 still. And I've got to do that here. Okay. So, should we go straight for it? That means that TR divided by TR plus 1 is going to equal... Now, first things first, we need to write this down in a more sensible form. And I think this is given in the formula book, but it's actually 50 factorial over, this is what the NCR function is, R factorial 50 minus R factorial. And then I'm going to times by those things as always, as before. On the bottom, 50 factorial over R plus 1 factorial, and then it's actually going to be 50 minus R plus 1, which is in fact going to become 49 minus R factorial. This will be a bit clearer for this next part. If I expand this bracket, I would get 50 minus R minus 1. So yes, I'll get 0.85 to the 49 minus R. I've done the same thing really, I just did it without, just went straight for it here. Times 0.15 to the R plus 1. Okay, that is obviously not simplified to what we need to, but we're on our way now. First things first, we can actually cancel these two out. I can sort of divide top and bottom by 50 factorial. So these are replaced by just 1 in this case. And then in fact, I can cancel out a bit like when you have powers, like x squared at the top and x cubed at the bottom. I've got one extra 0.15 here, so I can cancel this out with this, and I'm just left with 0.15 on the bottom. And up here it's very similar. I've got one extra 0.85 up here, so I can cancel this out with that. Okay, so I've got 0.15 on the bottom still, 0.85 on the top. Right, what next? Well, I'm sort of dividing the top by a fraction. What we can actually do is basically swap these two around. I can imagine timesing the top and the bottom by this and by this. And this is what will happen. It will become r plus 1 factorial 49 minus r factorial times 0.85 on the top. And then r factorial 50 minus r factorial times 0.15 on the bottom. If I've done that too fast, okay, let me give you another little example. If I had, say, 1 over x divided by 1 over y, I can imagine timesing top and bottom by x. So if I did that, it would cancel out here, and I'd get 1, and on the bottom I'd get 1 over x over y. I could then do the same by timesing top and bottom by y, so it would become y. When I times the bottom by y, they'd cancel, maybe x. That's all I've done. I've basically flipped them around because they're 1 over this, 1 over this. I've done that to make life easier because now I don't have any fractions within my fractions and I can finish cancelling out, and I'm not far from this final answer. You can almost, you might not be able to see it yet, but I've got an r plus 1 on the top and a 50 minus r on the bottom. Okay, next thing that you need to be aware of is that r plus 1 factorial is actually equal to r plus 1 times r minus 1 and so on, but it's actually r plus 1 times r factorial. So that means that this is going to cancel with this to just leave me r plus 1. It's just an extra 1 in there. And the same applies here. I've got 50 minus r times 49 minus r factorial here. So this cancels with this just to simply leave 50 minus r. I didn't say this question was easy, did I? Okay, all we need to do to finish is work out what 0.85 divided by 0.15 is. And it's 17 over 3. So this is going to become 17 r plus 1 over 3, 50 minus r as required. For me, that is the hardest bit of the whole question. Because it's you know, typically when we teach this, because the syllabus has changed and do a lot on your calculator, you might not go into lots of detail, or you know, just skim over these kind of ideas and how you cancel out factorials. It's like, you know, it hardly ever comes up, so it's not a big topic that is taught, but here it is expected to be dealt with, and I have tried to explain what's happened. So part 1 was not nice because it was either trial and improvement or normal approximation. You have to realize to do that. Part 2 is the trickiest bit. The good news is sort of once we've got this, even if you couldn't do part 2, you can take a look at part 3, and I'm going to talk about part 3 now. For the final part of this question, we now have the number of days when Paul's trained to work as late in the 50-day period is modeled by random variable x. So we're bringing back the binomial distribution aspect. So first thing to say, and actually I'm just going to come down here where I've put the question, is that now we've got the x follows the binomial distribution 50, 0.15. Find the values of r for which this is true. Well, in fact, we've we've done the hard work already, because this thing here, I did mention it before, is the same as TR. That is what TR is equal to. And this is TR plus 1. So we are trying to solve TR less than or equal to TR plus 1. Now both of these are positive, so I don't need to worry about changing the sign or anything. I can divide through by TR plus 1, and then I'm just trying to solve this. But we've just shown that the thing on the left is equal to that. So that's what I want to solve. 17, suddenly this becomes a lot nicer. We've got just a fractional equation to solve. 17r plus 1, 3 times 15 minus r less than or equal to 1. Multiply through by the denominator. So actually we're kind of back to, yeah, a nicer form. Sort it out, we're going to get 20r less than or equal to 133. .65. Okay, but r, remember, don't forget, r is like a whole number. It's the number of days the train is late r times, so it can't actually be 6.65. It's got to be 6. It's got to be overall 0 less than or equal to r less than or equal to 6. You get away with just writing the bit on the right, but that is going to be the situation for which the probability that x equals r is less than or equal to probability that x is equal to r plus 1. Okay, hence find the most likely number of days on which the train will be late during a 50-day period. Well, this actually follows from part A, because it must be that the probability that x equals 6, remember that's when I let r equal 6 in here, we've just shown that it's less than or equal to the probability that x equals 7. Actually, it's going to be less than. But the probability that x equals 8, because because it didn't continue, because we stopped at this point, it must actually be that 7's the maximum, basically. That's what this question's getting at. It's also, so overall for B, the most likely number of days is going to be 7. Actually, just out of interest, I think if we found the mean of this binomial distribution, 50 times 0.15, it'd give us 7.5. Okay, so yeah, maybe not, but that's the highest probability, and that's what we get as the final answer. Okay, well done for watching all of this, and I hope it makes sense. I hope it makes more sense than the mark scheme did. If you're looking at that, I've talked through all the different things. Trial and improvement, normal approximation, this bit here, and then finally, like using that idea to solve an inequality and get the final answer. Oof.